All right. Welcome back, everyone, for another deep dive. Today, we're going all the way down into the brain
Oh, yeah.
for a look at one of the most fundamental processes that make our brains work,
Yeah.
action potentials.
These are so cool.
Have you ever stopped and really thought about
Yeah.
how your brain actually thinks?
No way.
Like, what's physically happening in there to make all those thoughts and feelings and actions,
Yeah.
even just being able to listen to this podcast right now,
Right.
all comes down to these tiny little electrical signals
Yeah, and it's way more.
zipping around in your head.
It's actually way more than just electricity. It's this whole carefully orchestrated dance of ions that are moving across these membranes.
Okay, whoa, whoa, whoa.
It's why
Back up for a second,
Yeah.
because I know we have some listeners who are maybe tuning in for the first time or haven't
Right.
dug into neuroscience before.
Okay, sure.
So what exactly are we talking about when we say action potentials? Like, what are they in the simplest terms?
So basically, action potentials are like the language of the brain.
Okay,
They're the electrical signals that neurons use to communicate with each other.
gotcha. So
Yeah.
each neuron is sending out these little messages
Exactly.
to other neurons using these action potentials.
Yeah.
Okay, I like it so far, but I think I need a visual to really wrap my head around this.
Okay, sure.
Can you give us an analogy?
Okay, so imagine a line of dominoes all lined up, ready to go.
Okay, classic.
Each domino is like a little section of the neuron's membrane.
Okay, the outer part of the cell.
Exactly. And when one domino falls,
Yeah.
that represents the change in electrical charge that happens during an action potential, and that falling domino triggers the next one to fall, and so on down the line.
Ah, I see. So it's like this chain reaction happening.
Exactly. A chain reaction of electrical changes that travel down the neuron.
Okay, that's a really cool visual. So what is it that causes that first domino to fall?
That first domino gets ticked over when the neuron receives a signal from another neuron.
Okay, so a message comes in.
Exactly. A message comes in, and it causes special channels in the neuron's membrane to open up.
Okay, and what are these channels?
They're kind of like tiny little gates that control the flow of charged particles called ions in and out of the neuron.
So these ions are like the messengers or something.
They are. They're what actually carry the electrical charge.
Oh, cool.
So when enough positive ions flow into the neuron through these channels, it's like giving that first domino a good hard push, and that triggers the action potential.
Okay, so this is what you were talking about before with the dance of ions, right?
Exactly.
It's not just like electricity flowing through a wire. It's this very precisely controlled movement of these charged particles.
Precisely. And that's what makes it so fascinating.
This is already way more complex than I thought,
Yeah.
and we're just getting started. But one thing that's always blown my mind about action potentials is how incredibly fast they travel. We're talking meters per second. How is it possible for these signals to move so quickly and efficiently over these sometimes really long distances?
That's where our domino analogy really helps. Remember how I said each domino represents a section of the neuron? Well, it's not the same electrical pulse traveling the entire length of the neuron. It's more like a chain reaction, where the change in electrical charge in one section triggers the next section and so on down the line. And this happens along the axon, which is like the long cable-like part of the neuron.
Ah, that makes total sense. So each section is kind of like a little booster,
Yeah,
keeping the signal going strong all the way down the line.
exactly. And that's how the action potential can maintain its strength and speed, even over really long distances.
Okay, but I'm thinking about those dominoes again.
Yeah.
They only fall in one direction.
Right.
So is it the same with action potentials? Can they ever go backward?
That's a great question. And it brings us to another really important concept, the refractory period.
Okay, hit me with it.
So after a section of the axon has fired an action potential,
Yeah.
it needs a little time out
Okay.
to reset before it can fire another one.
Makes sense.
And this refractory period ensures that the signal only travels in one direction.
So a one-way street.
Exactly.
Yeah.
Prevents any kind of chaotic back and forth signaling.
Wow. So there's a built-in system to prevent signal traffic jams in the brain.
Yep. The brain is incredibly organized.
That's amazing. But hold on, there's got to be more to it, right? It can't just be this simple chain reaction.
Oh, you're absolutely right. There are other mechanisms that help to speed up signal transmission.
Okay, like what?
Well, many axons are covered in this fatty substance called myelin.
Oh, yeah, I've heard of that.
Yeah, think of it like insulation around an electrical wire.
Okay.
And this myelin sheath allows the action potential to jump between gaps in the insulation, a process called saltatory conduction.
Saltatory conduction, that sounds fancy.
It's pretty cool. And this jumping significantly speeds up the signal transmission.
Wow, the neuron has so many tricks up its sleeve to ensure those signals get where they need to go quickly and reliably. I'm loving this. But okay, back to our domino analogy for a sec. Once all the dominoes have fallen, someone has to set them back up, right?
Ah.
So how does the neuron reset itself after an action potential? How does it go back to its resting state?
You're exactly right. Someone has to reset those dominoes. And in the neuron, that happens through a process called repolarization.
Repolarization.
So remember how depolarization is when those positive ions rush into the neuron?
It triggers the whole thing.
Right. Well, during repolarization, different ion channels open up, allowing positive ions to flow back out of the neuron.
So it's like the opposite.
Exactly. It brings the electrical charge back down.
Okay.
But here's the thing. It actually overshoots a bit, going below the neuron's resting state, which we call hyperpolarization, before finally settling back to normal.
So the neuron gets a little too excited, then has to calm down.
Aha.
And it even dips below its chill state before recovering.
You got it.
That's kind of like after a sugar rush, you crash even harder.
Right.
We've all been there.
Totally.
But on a more serious note, what happens when something disrupts this whole intricate dance of ions?
That's when things can start to go wrong.
Yeah.
For instance, neurotoxins, like the ones you find in certain animal venoms, can interfere with these ion channels.
Oh, wow. Like how?
Well, some venoms actually block the channels that are responsible for sodium ions,
And those are important for...
which are essential for that initial depolarization.
Yeah, for kicking off the whole action potential.
Exactly. So without that influx of sodium ions, the action potential can't fire at all.
Oh, wow. So it's like someone glued the domino triggers down.
Exactly. And that can lead to paralysis because the signals from your brain can't reach your muscles.
That's terrifying. And I know you mentioned earlier that there are also disorders that can disrupt action potentials.
Yeah, definitely.
Doesn't epilepsy involve some kind of malfunction in this process?
It does. Epilepsy is characterized by these abnormal, synchronized firing of neurons in the brain.
Oh, wow. So like a whole bunch of neurons firing all at once?
Exactly. And this can happen for a variety of reasons.
Yeah.
But a lot of cases involve mutations in those ion channels.
Oh, so like the gates are messed up.
Yeah, particularly the ones that control the flow of potassium ions, which are really important for that repolarization phase, bringing the neuron back down to its resting state. And when those channels aren't working properly, it can make the neurons hyperexcitable, meaning they're more prone to firing uncontrollably.
And that uncontrolled firing leads to...
And that can lead to seizures.
Wow. So even tiny changes in these ion channels can have these massive effects on the whole system.
Yeah, it's a really delicate balance.
It's really amazing and a little bit scary to think about.
I know, right?
Like, how much is going on in our brains at any given moment to keep everything running smoothly?
It's mind-blowing.
So before we wrap things up, can you remind us again how all of this relates back to us, like to our everyday lives?
Okay, so let's take something you do every day, like picking up a cup of coffee.
Okay.
So your brain has to send signals down your spinal cord to the neurons that control your arm and hand muscles.
Right.
And those neurons release these chemicals called neurotransmitters,
Okay.
which then trigger action potentials in the muscle fibers,
Yeah.
causing them to contract, allowing you to lift the cup. So basically, every time you move, think, or feel anything, it's because of these action potentials firing away in your brain and throughout your nervous system.
Wow, that's amazing.
Uh-huh.
Something as simple as enjoying my morning coffee is like this incredible cascade of events, this intricate dance of ions happening in my brain and body.
Totally.
It's really mind-boggling. So what are some of the key takeaways you want our listeners to walk away with today?
I think the biggest one is that action potentials are the fundamental language of our nervous system.
Okay, yeah.
Like they're the basis for everything, our senses, our thoughts, our movements, everything.
It all comes back to those tiny little dominoes falling.
Right. And another important takeaway is just how complex this process really is.
Yeah, definitely not just a simple on-off switch.
No, it's this carefully orchestrated movement of ions across these membranes with all these different channels and phases and mechanisms to ensure that everything works properly.
And that even subtle disruptions in this process can have these really profound effects on our health and well-being.
Exactly.
It's like a delicate symphony playing out in our brains all the time.
I love that analogy.
And we've only just scratched the surface today.
Right.
There's so much more to learn about action potentials and how they all work together to create the amazing complexity of the human brain.
Absolutely. And, it makes you wonder what the future holds. Like, if we could one day figure out how to precisely control action potentials.
Oh man, the possibilities are endless.
Right. Could we treat neurological disorders more effectively? Enhance our cognitive abilities? The future of neuroscience is incredibly exciting.
Absolutely. Well, on that note, we'll have to leave it there for today. But this has been an amazing deep dive into the world of action potentials.
It really has.
Thanks so much for breaking it all down for us. I feel like I've learned so much.
Mm.
And for our listeners out there, keep those brains buzzing, and we'll catch you next time on the deep dive.
See ya.
Bye.